Hello students, welcome back to next session. It is on ideal cycles, reversed Carnot cycle. One more ideal cycle I am going to discuss in next session. This is the content for first unit. Introduction to refrigeration, unit of refrigeration, COP, ideal cycles, reversed Carnot cycle, ideal cycles, Bell-Coleman cycle, refrigerants and its desirable properties, refrigerants and its classification, refrigerants and its nomenclature. So these are the content for first unit. Once I start refrigerants, I can complete in one session all these topics, that is desirable properties, classification and nomenclature of refrigerants. So this is the first unit content, students. We are going to discuss today ideal cycles on reversed Carnot cycle. So before starting a Carnot cycle, let me introduce the air refrigeration system. Open air refrigeration cycle, this we are going to discuss now. In an open air refrigeration cycle, air is directly led to the space to be cooled. For example, it is refrigerator. In refrigerator, air is circulated where the space, in the space where the cooling process needed. Air circulates through the air cooler and then return to the compressor to start another cycle. So here, air is circulated in all the cycles that is happening in the refrigeration cycle. The pressure condition is air is supplied at atmospheric pressure to the refrigerator. So that is the pressure condition. Pressure is kept at atmospheric pressure. Compressor and expander size. Due to atmospheric pressure conditions, a large volume of air is handled by the compressor and expander. So here the working medium itself is the air. So to handle this air, we need the bigger size expander or compressor. So that is the requirement here. Moisture issue is there because air is always contains some humidity and moisture will form in the air. Moisture is generally carried by the air circulating through the cooled space. The frost formation issue also is there. The frost formation, the moisture is in the air leads to frost formation. So moisture is the main culprit due to which the frost is forming here. At the end of the expansion process, potentially clogging the line. So once the frost is formed in the line, then it will clog the line also. It will not allow the air to circulate comfortably. Solution we can provide: a dryer should be used in the open cycle system to prevent clogging due to frost formation. So we can use a dryer. Once we use dryer, it will dry out the frost, and frost actually melted, and that will be taken out of the system. What is a open air refrigeration cycle that we see here? A refrigeration cycle where air is used as the working fluid. The air itself is the working fluid here. Air is cooled, circulated through the refrigeration space and returned to the compressor back, and air is circulated. Air is circulated in all the cycles. No chemical refrigerants involved. So air itself is the working medium. So no other chemical refrigerants, external refrigerants are not required here. The working principle is very simple. Air is compressed by the compressor. So this is the first stage. Compressed air is cooled in the cooling system. So cooling system it cools the air, and air expands in the expander, reducing temperature. So wherever we have compression process, there will be a temperature increase in whatever medium we are compressing. So that should be cooled and that should be circulated here. The cooled air is released into the refrigerated space. Air recirculates back to the compressor. So now we are starting from compressor and we are ending in the same compressor for this particular cycle. So one cycle happens in these steps and next cycle starts once the air reaches back to compressor as normal air. Again air will be compressed and again air will acquire a higher temperature, and that should be cooled in cooling system, and then it should be expanded and further the temperature should be decreased, and then the cooled air is circulated in the refrigeration space, and then it is taken back to compressor. So this is the cyclic process happens in air refrigeration system. So the main components here, this is the simple block diagram. We can see here we have a compressor, and from compressor the compressed air is sent to the cooler, and from cooler it is sent to expander. From expander it is sent to refrigerator space. So this is the cyclic process happens, and the main components here obviously will be the compressor. It increases air pressure. Cooler removes heat from compressed air. Expander expands air lowering temperature, and refrigerated space area where cooling occurs, and dryer it removes moisture to prevent frost formation. So these are the cyclic process, and these are the components used in all cycles. Advantages of open air refrigeration system is it uses air as the refrigerant and it is eco-friendly, and we are not using any chemicals here. Simple system with no chemical refrigerants, works efficiently at a high altitudes, even it is useful in aircraft use. No risk of refrigerant leakage or contamination. Disadvantages are it requires large compressors and expanders due to low air density. Moisture in air leads to frost formation. Frost can clog the expansion valve, reducing efficiency. Less efficient compared to vapor compression refrigeration system. In next unit, students, we are going to start vapor compression refrigeration system, and that is the widely used refrigeration system everywhere that we are going to discuss in unit number 2. Moisture and frost problem. As I mentioned, frost formation is the biggest issue here in air refrigeration system. Air contains moisture which turns into frost when cooled. Frost accumulates at the expansion valve, blocking airflow. So solution is, as I said earlier, we have to provide a dryer to remove moisture before expansion. So moisture that contains in the air should be removed before sending it to expansion process. So applications, aircraft refrigeration system, it is normally used in cabin and engine cooling in aircrafts. Military applications, cooling electronic equipment. Industrial refrigeration, Opal cycle cooling system. So these are the major applications. Apart from this, we have many other applications also. Closed or dense air refrigeration system. So next type of refrigeration system, it is closed or dense type. It is also known as dense air refrigeration cycle. In a closed or dense air refrigeration cycle, the air is passed through the pipes and component parts of the system at all times. So the air is circulated in pipes instead of open space. The air in this system is used for absorbing heat from another fluid, say brine. So brine is nothing but a concentrated fluid. It is a very highly concentrated fluid, and this cooled brine is circulated into the space to be cooled. The air in the closed system does not come in contact directly with the space to be cooled. The closed air refrigeration cycle has the following thermodynamic advantages. The first one is it can work at a suction pressure higher than that of atmospheric pressure. the low volume of air handled by the compressor and expander is smaller compared to an open air refrigeration cycle system. So this is the very good advantage. We can use a compact size expander and compressor. The operating pressure ratio can be reduced, which results in a higher coefficient of performance. So COP can be higher than the open air refrigeration system. Air refrigerator working on reversed Carnot cycle. So let us start the reversed Carnot cycle here. What is reversed Carnot cycle? It is obviously a ideal cycle, which is not an actual cycle. The Carnot cycle is the most efficient thermodynamic cycle because it is ideal cycle, and we keep this as a reference cycle for other thermodynamic processes. When reversed, it acts as a refrigeration cycle. So the reversed Carnot cycle we are going to use here, we are going to employ here, used as the ideal benchmark for refrigeration systems. So this is the ideal reference, and with which we compare our actual refrigeration system and everything, the performance, coefficient of performance, everything we are going to compare with this ideal cycle. Why we use reversed Carnot cycle? So why we should use this? Because a heat engine working on the Carnot cycle has the highest efficiency in in theoretically only. In theoretically, we are having the highest efficiency when we use reversed Carnot cycle in a heat engine. A refrigerating system on the reversed Carnot cycle achieves maximum possible coefficient of performance. So, as highest efficiency in case of heat engine, here in refrigerator we are having the highest coefficient of performance. So that is the biggest advantage. Even though it is theoretical cycle and ideal cycle, whatever actually we produce, we can compare our performance, our system performance, the system that we develop, and we can compare that with the ideal cycle, that is reversed Carnot cycle. Though impractical to build, it serves as a theoretical standard. So it sets a standard. So that is the advantage here with reversed Carnot cycle. The working principle: the reversed Carnot cycle absorbs heat from low temperature region. So this that is why it is reversed Carnot cycle. It absorbs heat from low temperature region. It rejects heat to high temperature region. The working medium air undergoes compression as well as expansion processes. No real world system can perfectly follow this cycle, but it helps compare real systems. So we can compare our developed systems. So this is the cycle, and these are the two diagrams. I can explain all this with the four steps. There are four processes happening. So this is pressure PV diagram, temperature TS diagram. So this is TS diagram and this is PV diagram, pressure volume diagram, and the temperature entropy diagram. The cycle is represented on PV diagram and TS diagram. So at point 1, P1, that is pressure is P1, volume is V1, temperature is T1. So similarly, we have the entropy is also in a TS diagram. So all these four parameters are similar for other P2, P3 and P4. So there are 4 points we are going to discuss here. So the first process is taking place isentropic compression. So isentropic compression process is happening from 1 to 2. From 1 to 2. So this process is isentropic. Why it is isentropic is here it is happening at a constant entropy. So that is why it is known as isentropic process. From 1 to 2 it is happening and here if you see the entropy is constant. So this is entropy is constant, isentropic compression process. The air is compressed isentrophically by the curve 1 to 2. So from 1 to 2 on PV as well as in TS diagram. So temperature and entropy diagram. During this process, the pressure of air increases from P1 to P2. So you can see here pressure is getting increased, but volume is getting decreased. The specific volume decreases from V1 to V2. So this much decrease from V1 to V2. The temperature increases from T1 to T2. So temperature is increasing from T1 to T2, and we know that during isentropic compression, no heat is absorbed or rejected by the air. So we are doing the only compression of air. So it is the no heat is either absorbed or rejected. So this is the first step happening. So from 1 to 2, that is isentropic compression process. In next step, isometric compression, isothermal compression. Isothermal compression process, the air is now compressed isothermally at a constant temperature. So from 2 to 3, you can see in TS diagram, it is constant temperature. It is only constant temperature. It maintains constant temperature by the curve 2 to 3 on PV and TS diagrams. During this process, the pressure of air increases from P2 to P3. So the pressure is getting increased. So you can see here P2 to P3. So pressure is getting increased, and specific volume decreases from V2 to V3, and the volume is getting decreased. You can see here V2 to V3. So volume, there is a huge decrease in volume. We know that the heat rejected by the air during isothermal compression per kg of air. So this is the isothermal compression of this process, reversed Carnot cycle. So here the Qk is equal to Q2 minus 3. So that is the area under 2, 3, 3 dash and 2. So here you can see 2, 3, 2, 3 dash and 2. So this is the total heat, that is the per kg heat rejected by air during isothermal compression per kg. We can calculate here using Qk with the area under these points 2, 2, 3, 3 dash and 2 dash. So this area gives you the heat rejected by the air. Then third process is happening isentropic expansion. So again, it is a entropic process. It is constant entropy process. So here from 3 to 4, entropy remains constant, and here what is happening? Pressure is getting decreased. So pressure, we are decreasing the pressure in expander. The air is now expanded isentropically as shown by the curve 3 dash and 4 on PV diagram and TS diagrams. The pressure of air decreases from P3 to P4. So here P3 to P4. So that is P3 to P4. A huge pressure drop is happening in expander, and volume increases. So here you see the volume is getting increased from V3 to V4 marginally. It is a small increase in volume, and temperature decreases from T3 to T4. So this is T3 to T4. There is drop in temperature. We know that during this isentropic expansion, no heat is absorbed or rejected by the air. So no air, no heat is, there is no change happening to the heat. So the last one is isothermal expansion process. It is isothermal, hence it is constant temperature process. So from 4 to 1. Now we have traveled from point 1 to 2, 2 to 3, 3 to 4. Now we started traveling from point 4 to 1, that is 4 to 1. It is isothermal expansion process. the air is now expanded isothermally at a constant temperature T4 equal to T1 as shown by the curve 4 to 1. So this is 4 to 1, and what is happening? The volume is getting increased from 4, that is V4 to V1, volume is getting increased, and pressure again there is a decreasing trend from P4 to P1. So the pressure is getting decreased, but the temperature remains constant. The temperature remains constant, and we know that the heat absorbed by the air or heat extracted from the cold body during isothermal expansion per kg of air is equal to QA equal to Q4 minus 1, that is area under 4, 1, 2 dash 3 dash curves. That is equal to T4 into S1 minus S4 equal to T3 T4 S3 minus S4 and T1 S3 minus S4. And we know that the work done during the cycle per kg of air, the work done can be calculated as work done is heat rejected minus heat absorbed, that is QR minus QA, that is Q2 minus 3, 2 to 3 and Q4 to 1. So this is QR, the energy, the heat energy that is reduced, that is rejected, that is Q2 to 3 process, and heat absorbed is from Q4 to 1. That is equal to, in terms of Ts, T2 S2 minus S3 minus T1 S3 minus S4, that can be rewritten like T2 minus T1 into S2 minus S3. Thus, the coefficient of performance of the refrigeration system working on the reversed Carnot cycle, that is equal to COP refrigerator is equal to heat absorbed by work done, that is QA minus QR minus QA. So QA by QR minus QA, that is equal to Q4 to 1, Q2 to 3 minus Q4 to 1. So we can calculate the COP of this refrigerator using this formula in terms of Q. In a refrigerating machine, heat rejected is more than heat absorbed. COPR equal to T1 S2 minus S3 T2 minus T1 into S2 minus S3. So we can we can just simplify this like this: T1 divided by T2 minus T1. Though the reversed Carnot cycle is the most efficient between the fixed temperature limits, yet no refrigerator has been made using this cycle because it is theoretical cycle only, or it can be ideal cycle. It can be a ideal cycle. This is due to the reason that the isentropic processes of the cycle requires high speed, while the isothermal processes require an extremely low speed. So because this is the reason, students, you see here, the isentropic process requires a high speed, and while the isothermal process requires extremely low speed. So both are quite opposite. So this variation of speed of air, it is impossible to achieve in practice. So that is the main reason why it remains as theoretical cycle. COP pump equal to COP R plus 1. So COP of pump, coefficient of performance of pump, is always higher than COP of refrigerator. So that is plus 1 should be added. So here T1 by T2 minus T1 plus 1 equal to, so we can solve this, and T2 divided by T2 minus T1. And COP or efficiency of a heat engine, and we can have this for heat engine as well as. So for heat engine, it is WR by QR equal to T2 minus T1 S2 minus S3 divided by T2 into S2 minus S3, that is equal to T2 minus T1 divided by T2, that is equal to 1 by COP of pump. So once we know the COP of pump, we can calculate COP of heat engine also. So these are the relations between these three. the COP of refrigerator, COP of pump, COP of heat engine. So these three are mutually related also. Temperature limitations for reversed Carnot cycle. So here COP of reversed Carnot cycle of refrigerator can be calculated in simple relation, that is T1 divided by T2 minus T1, where T1 is the lower temperature refrigeration temperature, T2 is the higher refrigeration temperature. And here ways to improve COP. We can improve the COP by means of decreasing T2, that is lowering cooling medium temperature increases the efficiency, or increasing the T1 by increasing T1. So this is obviously it is on numerator. If you increase this, definitely COP will be increased. So higher refrigeration temperature improves performance. So limitations are T1 and T2 cannot be varied freely due to system constraints. It cannot be varied freely. T2 depends on cooling water air available for heat rejection. T1 is dictated by the refrigeration requirement only. So these are the limitations when we wanted to adjust this T1 or T2, and these are the limitations. Temperature limitations for reversed Carnot cycle. Heat transfer occurs correctly only when the higher temperature T1 is greater than the cooling temperature T2. So this is the heat transfer occurs, and the lower temperature is below the substance to be cooled. Effect of cooling medium, that is T2. When T2 is lower, there will be higher COP. When T2 is higher, lower COP. That is in terms of summer and winter, we can classify this. Carnot refrigerators work more efficiently in winter than summer. Effect of refrigeration application temperature. Higher refrigeration temperature obviously yields higher COP. Example, ice making at 0 degrees Celsius is equal to lower COP, and air conditioning, that is 20 degrees Celsius or 40 degree ambient temperature, there a higher COP is required. And conclusion, we can conclude this like this: a domestic refrigerator has lower Carnot COP than a domestic air conditioning system COP. So this is the conclusion we can make using these limitations of reversed Carnot cycle. Importance of reversed Carnot cycle. Theoretical benchmark defines the upper limit of efficiency. Performance comparison used to compare real refrigeration cycles guides the system optimization. It helps in improving the real systems. So once we see the higher coefficient of performance in ideal cycle, definitely we will work to achieve that. Limitations of reversed Carnot cycle, not practical to implement. It is not a practical cycle. We cannot implement practically. Requires perfectly reversible processes. Perfectly reversible is impossible in practice. Assumes ideal conditions, no friction, perfect insulation, everything. Real refrigeration system use modified cycles. Vapor compression cycle is used instead. So these are the limitations of reversed Carnot cycle. And we see problems. I wanted to solve few problems on this. Let me take up in next session, students, as well as I said earlier sessions, in earlier sessions, please refer the books, that is CP Arora, Bellani, as well as Kurmi. Kurmi is a simple book. Definitely we can follow that book, students. We stop here, and in next session we are going to see the different kinds of problems on this particular reversed Carnot cycle. Thank you, students. We stop here. We will meet again in next session very soon. Thank you. Thank you.